Hello, everyone, and welcome to the Mindscape podcast. I'm your host, Sean Carroll. As I will mention very briefly in today's podcast, when I was a kid growing up, I knew that I wanted to do science. In fact, theoretical physics is what I knew I wanted to do from a very early age. But theoretical physics, Einstein's equation, quarks, things like that, this is not something anyone in my family or circle understood. They did understand that it was somehow related to space and astronomy and things like that. So I would be frequently given, telescopes or books about astronomy as gifts, which is great. I love that stuff too. It just wasn't what I actually wanted to do for a living. But as a result of this, circa, 1980 was kind of my peak knowledge about modern astronomy, even though I went on as an undergraduate and a graduate student to be an astronomy major, get a bachelor's degree as well as a Ph.D. in astronomy. By then, I was actually focusing more on learning fundamental physics. So I had to sit through my required courses in astronomy, but I wasn't in my spare time catching up on the most recent discoveries about planets and stars and galaxies and stuff like that. And even today, I just as much as anyone else follow the news items. I get to talk to my colleagues, it's true, so I probably get more inside scoop than the average person. But I'm absolutely not at the cutting edge of what's going on broadly in astronomy more than many people are. So since I did have that knowledge back in the 70s and 80s, it's always fun to catch up on what's been going on since then. And when it comes to something like planets, we have just learned so much more about the planets, both in our solar system as well as exoplanets, of course, than we did back then. I mean, not only was Pluto a planet back when I was still learning this stuff, but we had just started in the 1970s sending spacecraft to other planets. We had learned, to our surprise, that the atmosphere of Venus was kind of inhospitable. We knew that even before we sent the spacecraft there, but it was a surprise when we learned it. We were still hoping to find life on Mars of some sort, not just little microbial life, but maybe something more exotic. The very first landers, the Viking landers, were sent to Mars, but also there were missions sent to Venus that just plunged right in, even missions sent to Mercury, as well as, of course, famously, the Pioneer and Voyager missions to the outer planets. So it was a very exciting time back then, but so much more has happened now, landing on all sorts of planets, investigating them, measuring their properties with much greater precision. So today, we get to catch up on some of this knowledge with Sabine Stanley, who is actually an astronomer at Johns Hopkins and has recently come out with a book published by Johns Hopkins University Press called What's Hidden Inside Planets. And the idea is, of course, that there's the atmosphere and the outer layers of planets, but there's also the very fun interiors of planets, which is kind of a place where we know a lot, but much less than we would like to. Even the Earth, as we will learn in the podcast, we know things indirectly, not directly. We have not journeyed to the center of the Earth in reality as much as we like to imagine doing so in fiction. So it's always fun to learn how clever scientists have been to figure out what's going on in places we can't see, including the ground right beneath our feet, and extending that knowledge then to other planets, making predictions for what their gravitational fields should be, what their magnetic fields should be, watching those predictions go wildly wrong, updating our models and going, oh yes, we forgot about sulfur. That's kind of important, or something like that. So there's a whole mess of things we're going to learn. And we're going to learn about the diamond iceberg floating on liquid oceans in cold planets far away, and how all that stuff happens and how much more we have yet to learn. So let's go. Sabine Stanley, welcome to the Mindscape podcast.
Thanks so much for having me.
So we're going to talk about what's inside planets. I wanted to set the stage just by remembering, when I was a kid, we had terrestrial planets and we had gas giants, right? And of course, these days, we kicked Pluto out and we've discovered exoplanets and things like that. Is it still, though, basically true that we have those two categories, or has our space of possible planets to think about grown bigger?
I definitely think the space of possible planets has grown bigger, right? Even in our own solar system, we even now with the giant planets, we know that there's Jupiter and Saturn, which are these gassy giant planets. Then you've got the ice-rich planets, Uranus and Neptune, so they can be quite different. We have metal worlds in our solar system with 16 Psyche, this asteroid that the Psyche mission is going to go to as well. So there's a lot of variety even here in our solar system, and everything we've found outside of our solar system just shows us how many more possibilities there are.
Well, my not quite expert impression from the exoplanet research is that we have been surprised by various properties of planets. Have we actually discovered new kinds of planets?
Yeah, absolutely. It's really interesting to think about. I remember when I was learning this stuff in undergrad, that we had this sort of real belief that we understood how planets formed, and that wherever we would look, it should be that you'd have the rocky planets in kind of the closer to the star system, and then you'd have the gas giant planets further out. And then boom, the first exoplanets we see, suddenly you've got something bigger than Jupiter orbiting closer than Mercury does in our own solar system. So just early exoplanet discoveries just really showed us that we needed to kind of rethink how planet formation occurs and what the possibilities are out there.
And I guess it made sense to think that back in the day, right? Because we thought that in the early stages of the formation of the planetary system, the atmosphere would get blown off of the planets. I mean, I'm a very theoretical physicist here, but I have this feeling that, the inner planets are rocky because that's all that was left, and the outer planets are gaseous because they could keep their atmospheres.
Mm-hmm. It's a little bit, I would say it's a little bit different. It's more that the inner planets are rocky because there was no gas. They couldn't grow fast enough to collect the gas, whereas the outer planets could grow faster because they had more building blocks. But I think the key thing that we learned from looking at these exoplanet systems is there was a process that we had kind of thought wasn't that important for our own solar system, but turns out to be important in other solar systems, and that's planetary migration, the fact that planets can move their orbits over time. So.
Well, I will, we can jump around. We don't need to be logical order here for what we're talking about. So I'll confess, when I was looking into your book and thinking about this podcast, I never knew that people thought that Jupiter might have started its life much, much closer to the sun than it is now.
Yeah, it's possible that it actually moved a lot. It started further out, then came in kind of closer to kind of where Mars currently is, and then switched again and started moving out again. And Uranus and Neptune might have actually switched places. It used to be that Neptune was closer than Uranus. So these are all reasonable possibilities based on what we see in terms of the orbits of a lot of the asteroids and Kuiper Belt objects out there in the outer solar system right now.
Is there some just human scale difficulty? Because when we see the solar system, it seems like more or less the same from when we're born to when we die, and extrapolating it back a billion years is kind of hard.
Yeah, I think that's a natural issue that we always have with things that are on such long time scales or really far away, is putting it on the scale. But I know this is kind of in a separate vein, but I think it's interesting to think about the fact that it's possible that Saturn didn't have rings when there were dinosaurs on Earth. So things do change, right? Even in sort of the timescales we're used to trying to comprehend, even if it's not on a human lifespan timescale.
So let me just quickly get your opinion. Do you think Saturn did have rings back when the dinosaurs were around?
Oh gosh, I think it's not something to have an opinion about. I think it's really interesting to think about how the rings are populated and how they change. I think we just need more data to study that.
And what is here is an opinion question. Pluto, planet or not?
Okay, here's my answer. It's not a planet, and that's okay. Pluto is just really cool. It was such an interesting object that it started its own class of planetary object, the dwarf planet. So why would you want to be a planet when you can just start your own class of planetary objects? So,
I will confess, I've said this before, but in the early days, I was against kicking Pluto out of the planet club on the basis of, the idea of a planet is something we human beings made up. We can grandfather in Pluto. But I had Mike Brown, who was a good friend of mine from Caltech, on the podcast, and I read his book, and I did change my mind, like a good scientist should. So I think that the scientists are right about this one.
I agree.
Okay, so let's get to what you actually do for a living, as I understand it, the interiors of planets, which is a little bit harder than the exteriors, right? We can't actually see them. I presume we start by thinking about the Earth and what we know about its interior.
Yeah, absolutely. You know, it's frustrating because when you try to think about what's going on inside a planet, your first instinct is, you know, let's dig in there and get some samples and try and figure that out. But it's just it's impossible for Earth, right? The furthest we've ever drilled into the planet is under 10 kilometers, right? It's basically nothing, or under 10 miles, sorry. It's basically nothing for a planet with a, say, 6,000 kilometer radius, right? So We're just kind of getting at the skin here. So we have to be really sneaky and clever in how we figure out properties of the interior of the planet, do a lot of things that like doctors do to figure out what's wrong with you when you go to the doctor, right? Hopefully they don't drill first and kind of figure out things later, right? So it's a lot of honing techniques to give us the information we're looking for the interiors of planet.
It's kind of sad that we've only gone down less than 10 miles. Is that ambition the planetary scientists have? Like particle physicists want to build a bigger and bigger collider. Do planetary physicists want to dig deeper and deeper?
I don't think it's so much nowadays that there's this goal of digging. We want to learn more and more about the deep interior, but we're open to the fact that there are better, sometimes more efficient other ways to do this, right? So nowadays, I think we rely a lot on the combination of sort of non-digging type technology, right? Relying on sensors and waves to study the interior, but also the fact that we can get samples can come up from depth. Whenever diamonds come to the surface, some of them actually preserve bits of the mantle inside of them, like as inclusions, and so we can learn about things that way. Meteorites tell us about the interiors of asteroids and other bodies out there. So we're willing to get the information however possible. I'm not sure that we're all kind of hell-bent on digging anymore.
Well, I'm sorry just to follow up on this crazy scenario, but if I did want to build a little robot that had a drill and could just dig down deeper and deeper, what is the obstacle? Is it the heat or the density or the power source?
So it's a combination of the pressure and the heat, right? Every time you're going a little bit deeper inside the planet, temperatures are rising. Equipment doesn't like hot temperatures, doesn't like high pressures, humans don't like them. So it's harder to get down there to fix things as well, just as it is if you're going out into space. So it's the combination, right? If you think about sort of the deepest mines we have that humans can function in, right? You're talking about things that are in the 2 mile depth range, 1 to 2 mile depth range, right? So it's a combination of those two issues.
Okay, so we're stuck with being the doctor who cannot perform surgery. What do we actually do? How do we know about, I guess maybe what is the Earth's interior like? And then how do we know?
Yeah, so the Earth, which is kind of a good prototype or typical example of a rocky planet, the outer part of it is made of sort of magnesium silicates, what we would normally consider as rocky materials. And then the inner part of the planet is iron. So we have an iron core. In Earth, the innermost part of that, about the innermost 1,300 kilometers, is solid. And then you've got a liquid iron core for another 2,000 or so kilometers. And so you've got this separation, right? The heaviest stuff, the densest stuff is at the center. And then the outer layers are rock. And that's true for the other rocky planets as well. So how do we figure this all out? Combination of methods. One of the coolest methods to me to talk about, and the one that gives us a lot of information, is seismology. So every time there's an earthquake somewhere, sound waves essentially travel through the Earth, and we can record when they arrive at different locations on the surface. And those waves, whatever region they traveled through, the speed of the wave is completely related to the material properties that they're traveling through. So we can use that information at the surface and kind of backtrack all the waves that go through the Earth and learn about the material they pass through. That's how we learned that the Earth has an iron core, that the outer part of it is liquid. We can learn about phase transitions in the Earth's mantle. So when minerals change their structural properties into other physical arrangements, all sorts of stuff. So that's kind of been the sort of workhorse of planetary interior studies.
Obviously, I've heard that story before, and it does make sense, right? You have a sound wave traveling through, and it is kind of like what doctors do, whether it's a CAT scan or an MRI or whatever.
Yeah,
but
exactly.
But it still seems a little crude, I mean, hearing these sounds from earthquakes thousands of miles away and saying, okay, I have now inferred the internal structure of the Earth. I mean, what's our confidence level here?
So here's the amazing things. We have lots of earthquakes. They travel through different parts of the Earth. They travel in different directions through different materials. So with sort of modern day analysis techniques and computational methods, we can actually get a lot of really great data. We can see things like volcanic plumes coming up from the core mantle boundary all the way to the surface of the Earth. We can see subducting slabs, so places on the planet where one tectonic plate is descending back into the Earth under another one. We can see that colder material descending into the Earth almost all the way down to the core mantle boundary. So we're really at the point where we're getting like lateral structure. It's not just a depth as a density as a function of depth. It's really like imaging now of the interior.
So we're getting something like a 3D picture of what the Earth's interior looks like.
Absolutely.
And okay, so we have the core, the inner core and outer core and mantle are the three that I remember from high school.
Yep.
That's still true? Like everything else I learned in my high school science classes is not true anymore.
It's still true. It's just it gets more, the more we learn, the more we can break things up, right? Now the mantle's got the upper mantle, the lower mantle. You can talk about transition zones. You can talk about all fun sorts of phase transitions, stuff like that. But to a basic level, that's still accurate.
And which parts are liquid and which parts are solid?
So the only liquid part in the interior of the Earth is the liquid iron outer core. So there's about 2,500 kilometers or so near the center of the Earth that's liquid.
So the very core is also iron, but solid.
Yeah, that is correct. And there's an interesting property in the deep interiors is that so pressure is increasing as you're going deeper and temperature is increasing as you're going deeper. So the very center of the Earth, even though the temperature is much hotter than the outer parts of the layers, it's solid because it's pressure frozen. It's basically squeezed so much that it has to be solid. So just a fun thing when you're thinking about how things are different inside the Earth than they are, say, at the surface.
And the mantle, I guess, this is part of my inner picture, which is probably faulty, but I think of it as what's coming up in lava and volcanoes and things like that, which looks liquid to me, but it's actually solid.
So yeah, this is such a common understanding that needs to be corrected, Good. Right? When we see it at the surface, yes, lava is liquid, but that's because you took something that was under really high pressure and you quickly depressurized it, right? So that material that's coming up at volcanoes, it wasn't liquid inside the Earth. It was solid. It just got depressurized so that then that expanded volume made it into a liquid.
Okay, but the Earth is 4-point-something billion years old. Should we be surprised that it's as active as it is, that it's still sort of churning around and plate tectonics and all that stuff? Why hasn't it settled down yet?
That's a great question. So yes, the Earth is very old. All the planets are, but all the planets we have some hints of some sort of activity on the inside. We're the only planet with plate tectonics, but you got Mercury's generating a dynamo in its core, which means that its core is still convecting and very active. You have tectonic processes happening on Mars. So the crust and the outer parts of the planets are shifting around in response to, like they're flexing in response to, say, thermal gradients or other tidal forces and stuff like that. The key thing with planets is all planets start out really hot. The centers of planets are much hotter than the space. And so they're all cooling. And most of the motions, most of the processes we see happening are a result of that cooling. And so that activity is the cooling. And it takes a really long time to cool down a planet. So that's why we're still seeing activity everywhere.
And part of that is that these interiors are not only iron, they have heavier radioactive elements that are still providing some heat.
That's exactly right. So you've got the initial heat of formation. When these planets formed, they stored a lot of heat inside, but planets also have uranium, thorium, these long-lived radionuclides that can actually generate heat today. About half of the heat coming out of the Earth today is coming from radioactive elements in Earth's mantle.
That always, again, my intuition fails me here, right? Because there's not that much uranium and thorium in there, but I guess there's a lot of volume in the Earth, so it's enough to keep it hot.
Exactly.
And how do we know how much uranium is in the middle of the Earth? Is it reverse engineering from how hot it is?
No, it's actually based on, so if we look at samples that we have of Earth, so it's mostly based on estimates we have from the crust or maybe the upper mantle. You take samples from there, you actually measure how much uranium and thorium or their daughter products that you have there, and from that you come up with estimates of what you think is in the Earth. It's a combination of just direct measuring and then also understanding, okay, so I've got a rock, and when it melts, does uranium and thorium prefer to be with this part of the melt or that part of the melt? So it's a lot of geology and geochemistry involved that can tell you where you should expect to find the uranium and thorium.
Yeah, it's always a reminder to me because as a physicist, I will sometimes teach general relativity. And it's this beautiful, pristine logical edifice, right? And I love teaching it. And then sometimes I'll teach cosmology, and it's a mess. Like every week you have to do something else, like thermodynamics and E&M and whatever, particle physics. I imagine that your job is even more of a mess than cosmology is in terms of all the different kinds of knowledge that come in.
Yeah, absolutely. But honestly, that's what I love about it. I love the fact that in order to make, to have progress in understanding the interior of the Earth and planets, you need to combine the sort of fundamental physics knowledge, the chemistry knowledge, the methods and like sensors and observational methods knowledge, right? It's a big puzzle, and you got to bring in all these different types of knowledge to get an answer.
Speaking of which, okay, we talked about the seismic information. I guess I should ask, is that more active or passive? Like, do we have detectors that were set up specifically to understand the interior of the Earth, or do we sort of piggyback off of the fact that we want to know where earthquakes are happening anyway?
So over time, there's been more and more interest in having seismic sensors basically all over the surface of the Earth. And there are these great sort of dense arrays of sensors. For example, all over the US, there's this moving US sensor network that goes around, and other countries and regions of the Earth are doing this as well. So we're very actively looking for putting up sensors so that we can measure when earthquakes happen, where they are. We are also kind of moving out into the solar system, right? We have had seismometers on the moon since the Apollo missions. They were turned off in I guess it was the early 80s. But we've very recently put a seismometer on Mars and been able to measure Mars quakes there, and from those Mars quakes, be able to learn about the interior of Mars as well. So I think there's a major move to using seismology on other planetary bodies because of the wealth of information it provides.
Cool. And I guess probably there wasn't a lot on the moon, or are there moonquakes all the time?
There are moonquakes all the time. So this is amazing. So, and a lot of the Artemis mission, there are plans to put new seismometers on the moon in different locations so that we can start studying these again. Moonquakes actually happen for a variety of reasons. Sometimes you have impact. So the moon is hit with meteors as well as Earth is and all other planets over time.
Sure.
So we can measure moonquakes from that. But there are also these very deep moonquakes. They happen much deeper in the moon, and they're actually caused by tidal flexing of the moon. So the moon experiences tidal forces just like the Earth does. Why we have tides, the moon has tides. And so we can actually measure rumblings in the inside of the moon from those tidal forces.
All right. And then what else besides seismic information do we use to learn about the interior of the Earth?
Yeah, so then take a combination of fields. So gravity fields, magnetic fields, those are probably the biggest ones there. So gravity fields, the fact that, when we teach our intro physics courses, we tell everyone, G is 9.8 meters per second squared on the surface of the Earth. That's not true. As you walk around on the surface of the Earth, the value of G actually varies, and it depends on how much mass is directly below you. And so we can measure those variations in gravity and use that to actually learn about variations in density below our feet. And so we can do this for other planets as well. There have been gravity missions sent to, basically any planet that we've sent a mission to, we have gravity data from.
Okay.
And from that, we can learn about the interior mass distributions inside planets.
In cosmology right now, there's a famous Hubble tension. We measure the Hubble constant in two different ways to get two different answers. I could imagine Earth's core tension, if you measured its properties seismically one way and then magnetic fields or gravitational fields another way. Is there any such thing on the horizon, or is everything completely compatible?
That's an interesting question. First of all, I'm frustrated with even though I'm not in the field, I hate that it's called a tension, because I'm like, it's not a tension. It's a complete like
the disagreement.
Difference, completely different numbers. That's not a tension. But anyway, going back to the Earth, I think it's much more that the methods are very complementary. So gravity tells you something about bulk stuff, right? The gravity field can't really tell you about what the density is at a particular location.
Sure.
But you combine that with the seismology, and the seismology tells you, hey, you have an iron core at the center. Then that you combine that with the gravity, and you can use that to really infer more details about stuff, right? So all the methods are really complementary. There isn't any tension that I can think of offhand. There are the latest tension that's interesting is with what seismology and gravity are telling us, for example, about what Mars's core is made of, and what we think is true about the material that was around in the solar system while planets were forming. So in Mars Insight mission, right, measures the radius of the core for the first time, very near the end of the mission. We were waiting for like the big one on Mars, and it finally came like a couple months before we were shutting down the mission. And from that, we were able to figure out the radius of Mars's core. And it's a little bit bigger than we thought we knew from gravity. But gravity tells you a bulk measurement. So essentially, if the core is bigger, it means that it has to be a little less dense, a little lighter than what we thought. But if it's a little lighter, that means that it combined with the iron in the core, there's some lighter elements. And it's really hard to kind of figure out how these light elements got to the center of Mars based on what we thought the building blocks of planets were. So that's kind of a little bit of a tension right now, although I think there are ways around it, and we just need to understand the geochemistry of planet formation a little more.
I think the better thing for you to do is to label it the Mars core crisis, and the grant money and the publicity will start rolling in.
I will take that advice. That's amazing.
And you mentioned something a little provocative before about mercury and convection and magnetic fields. So magnetic fields are obviously the other way, as you mentioned gravity and magnetism. What does the Earth's magnetic field let us infer about its interior?
Yeah, great question. So magnetic fields happen to be my favorite thing to talk about. And you can learn a lot from magnetic fields for any planet. So let's start with Earth. The key thing about magnetic fields, if a planet has a magnetic field, then first of all, you know it has to have a good electrical conductor somewhere on the inside, and that's great. Iron at the center of the Earth does that for you. You know it has to have motions in it. And so that tells you that, first of all, you have to have a liquid to have the motions be fast enough for this to occur, and there needs to be a power source for those motions. And so this is how we know, for example, that Earth's core, there's convection going on in Earth's core. It's trying to remove heat through that convection. And so that tells us a lot about how much energy and power is stored inside the Earth. So you learn a lot about the thermal evolution of a planet by knowing that it has an active magnetic field generated today. It gets generated by this dynamo action, right? Similar sort of process that runs your generators or your bike lights, but lots of information by seeing a magnetic field.
So the convection is presumably in that liquid outer core.
Absolutely.
And it really is just sort of a constant churning because of thermal disequilibrium somehow.
So yeah, basically it's like when you put a pot on your stove, bottom's hotter than the top. If you try to get heat through there faster than can be conducted through the material, you're going to get convection. So it's the same sort of thing inside the core of a planet.
And so in the absence of that, if you didn't have that, you would not have a magnetic field? There's no other way?
That's correct. Yeah, that is correct. So for example, Mars today doesn't have an actively generating magnetic field today. It doesn't have a dynamo, but it does have rocks on the surface that are magnetized, which tells us that it did have a dynamo in its past. So we've learned something about the thermal evolution of Mars 4 billion years ago by looking at these rocks on the surface that are magnetized.
But there's no convection going on in my refrigerator magnets.
So that's a different kind of magnet. So when you have permanent magnets, so the insides of planets aren't permanent magnets. These are what are called induction processes creating magnetic fields. So it's the moving around of currents that are creating new magnetic fields. It's not like permanent magnets like your fridge magnet.
Good. And so that does sound like a pretty consistent story overall. Like if we didn't know about the magnetic field, would the seismic observations have led us to conclude that part of the core was liquid?
So yes, so the seismic observations luckily can give us that information in a completely different way. It's because a certain type of wave doesn't travel through liquids. So these shear waves that are called S waves inside planets, they don't travel through liquids. So when we see them disappear in our seismic records, we say, they must have gone through a liquid. But what magnetic fields can add to it is first of all, the motions. We can't tell that there are motions in the core without magnetic fields. And the other thing that magnetic fields can really do for you is tell you about the history of a planet. So because the rocks on the surface record magnetic fields at the time they formed, that's why we learned about plate tectonics on the surface of the Earth and where the land masses were in the past and so forth. And exactly the same sort of thing on Mars. We could learn that the core of Mars is liquid from seismology, but we never would have been able to learn that it had a dynamo in its early history if it weren't for magnetic fields being recorded in the rocks.
And the magnetic field of the Earth does all these weird things, like it wanders around, occasionally it just reverses its polarity, right? And as far as I know, we can't predict when, and we're not exactly sure why.
Yeah, that's a great way of looking at it. So it's an interesting comparison when you think about the sun. So our sun also has a magnetic field, and that magnetic field also reverses, but it does so like clockwork every 11 years. Poof, reversal, right? In the Earth, we're aware of reversals because we have rock record that tells us that there are reversals in the past, but it's not periodic. But it's happened. If you were to take all the ones we know about and divide by the amount of time they've happened over, on average, every 500,000 years or so, the Earth's magnetic field reversals. The last reversal was about 750,000 years ago. So in some metric, we're a little bit overdue for a reversal, but it's also, a kind of non-periodic process. So it could just be normal right now.
It could be another 250,000 years before it happens.
Exactly. Yeah.
Would it be bad if it happened tomorrow? Would it break the internet?
It's an interesting question. As far as we know, again, having not lived through a reversal ourselves and been able to measure it, what we can see in the rock record tells us, first of all, that reversals probably take a bit of time. They might take somewhere on the order of 1,000 years or so to actually fully complete. So I like to hope that as humans, any of the complications associated with a reversal, we could actually adjust for, right? So the main issues we would have if a reversal occurs is actually due to our technology, right? So we rely very heavily right now on satellites orbiting the Earth. They do everything from GPS to navigation to all that stuff, right? Our magnetic field actually very much shields all of those satellites from the high energy particles that come from the sun, the solar wind, and cosmic rays. So during a reversal, the Earth's magnetic field actually decreases somewhat, gets more chaotic. And so satellites in orbit would actually be more susceptible to being hit by these high energy cosmic rays and solar wind. And so they could get knocked out, for example.
Okay.
So, but, if that happens on, say, a human lifetime scale, maybe hopefully we could change our technology in time to deal with that.
I do remember reading that over the last 150 years, the magnetic field has been diminishing slightly in magnitude.
Yeah, slightly, that's true. But it's interesting. If you look at a longer time record, it was actually pretty high recently. So the diminishing that's happening now is still putting us above the average over, say, the past 10,000 years. So I think we have to look at a longer time record before we can decide, is this some weird anomaly? Are we in the beginning of a reversal or not?
For the young people out there who are deciding on their future research careers, is understanding the Earth's magnetic field something that is still very much an ongoing project?
Absolutely. So there's different ways you can tackle this, right? So for people who really like sort of studying fluid dynamics and sort of nonlinear dynamics, chaos, that kind of stuff, there's understanding the fundamental processes involved. For people who really like observational studies, trying to get data now from satellites in orbit, lots of cool data analysis projects. We're really trying to understand the magnetosphere, the region surrounding Earth, because that's important for our understanding of space weather, and that helps us in keeping our technology going. And then, of course, for other planets, we're trying to learn about them from their magnetic fields as well. So yeah, there's lots of work to be done here. It's a very data-driven field, lots of use nowadays of, data science, machine learning, high computational models, lots of cool stuff going on.
And something you're implying is that both the plate tectonics on Earth and the magnetic field are kind of temporary. I mean, eventually those radioactive materials will decay away and the Earth will just cool off.
That is accurate.
All right, so we should enjoy the magnetic field while we have
yes,
it.
Absolutely. Maybe we'll find new ways to generate it or something.
Maybe.
Right? That's
the other thing that makes the Earth special here in the solar system is the moon, right? I mean, the moon is much bigger compared to the Earth than any other planet's satellite is. Do we learn about the Earth by studying the moon or vice versa? Or is there still a lot of uncertainty about how the whole thing came together in the first place.
Absolutely. So it's really interesting to me that, especially if you're thinking about the early history of Earth, right? You had mentioned Earth 4.67 billion years old. And the surface of the Earth is very young because we have plate tectonics. The surface gets recycled back into the interior. There's very little old rock on the surface. Fortunately for us, there's lots of old rock on the moon. And the Earth and the moon formed from the same sort of material. There was a giant impact very early in Earth's history. And so there's a lot of similarities between the Earth's material and the moon's material. And being able to look at the rock record on the moon actually tells us a lot about, first of all, the early solar system in general, but also about the early Earth.
Is that impact theory more or less the consensus these days?
Yeah, it's the only one that can explain all the observables at the moment.
I read that there was recently a claim that we could, so if there was an impact, then there was the proto-Earth and some other planet, the planet has a name that I forget now, came and smashed into us, and we can actually identify chunks of the planet inside the Earth right now. Is that credible?
So my understanding of that research is that we do computer simulations of that impact nowadays. So you take a body that was a Mars-sized body, believed to be, it's usually given the name Theia. And when it crashed into the Earth, you can ask the question, where did the material go? And you do find that some of the material from the impactor gets put inside the Earth. And so the question is, does it mix in all the way or so forth? And there have been some computer simulations of these processes that suggest that some of it ends up at the bottom of the mantle, kind of right above the core mantle boundary. And it turns out that we have these weird features in the mantle that we've learned from seismology that are down there. And so I would put it at the moment as a hypothesis with some simulation suggesting it's feasible, but there are potential other explanations for the materials that we see down at the core mantle boundary. So it's not definitive, I would say, at the moment.
But should we get the impression that the simple cartoon that we see of the cutaway Earth with the inner core, outer core mantle, the reality is not quite so pretty and symmetric as that?
Yeah, that's definitely true, right? It's never as pretty as the simple models.
And also the movie The Core was probably not realistic.
The movie The Core is my favorite movie in the whole universe, first off. But it is accurate to say that there are some things in it that are not realistic, but still a great, some of the stuff in there was fabulous.
That you got to take what you can get for Hollywood entertainment.
Exactly.
That's fine. Okay, so I mean, with the moon, what do we know about its interior? You said there are moonquakes. Does it also have a hot little core?
So the moon does have a core, but the core is much smaller than, for example, Earth's core is relative to the size of Earth. So the moon's core is only about 400 kilometers in radius, right? The moon's radius is about 1,800, what is it? The moon's radius, it's about 1,800 kilometers, 1,700 kilometers or so.
They can look that up, don't worry.
Yeah, so we'll Google that later. So it's a smaller core, and that actually makes sense when we think about how the moon formed, because the collision that would have created the moon, when you do a glancing impact, probably the core of the moon, of that Theia body, ended up more inside the Earth, and more rocky material from Earth's mantle and from Theia ended up in orbit around Earth, and that then created the moon. So it makes sense that there's less iron in the moon if it formed from that impact.
And it also, sometimes I worry when things make sense that I think I understand them, but I really don't. So it sounds like it makes sense that the moon is cooler on the inside and doesn't have a magnetic field and doesn't have plate tectonics just because it's smaller, in addition to the formation history. I mean, it should cool off quicker, right?
So this is interesting. Yes, it makes sense that way. However, we have to be very careful with reasoning like that. And there's a great story about the planet Mercury when we do reasoning like that. So the first mission that went to Mercury to study the planet in detail was Mariner 10 in the mid-1970s. And there's this great paper that came out a couple of years before the spacecraft got to Mercury. And it said, Mercury is a very small planet, which is true. And so it should cool down fast, which is true. And so it shouldn't have an active dynamo-generating magnetic field today because the core should be completely solidified. And then, boom, Mariner 10 gets to Mercury and measures an active magnetic field. And so luckily, right, and that's okay. Predictions are meant to be there as based on what our understanding of the theory is at the time. But after we actually saw the magnetic field, then scientists went back to the drawing board and they were like, okay, maybe the core is not pure iron. Mix in a little bit of sulfur in that iron and you change the melting temperature so much that you could actually keep the core liquid much longer. And so it was this actual data. I guess what I'm trying to say is data is really important before we use sort of just very basic principles to try and understand what's going on inside a planet. The details tend to matter a lot.
Are we lucky that Mariner was equipped with a magnetometer?
Yes, because there was no other way to know that from that. It was not until much later, just before the Messenger mission got to Mercury in the early 2000s, that we actually had another way to determine that there was a liquid core inside Mercury. And that was from a really interesting study of radar observations from Earth, looking at Mercury and seeing how the planet wobbles while it spins.
Okay.
And so because Mercury has this very elliptical orbit around the sun, its length of day essentially changes a little bit depending on how far it is from the sun. And we could actually measure that wobble and from that get the moment of inertia. And from that realize that the amount that the planet was wobbling meant there had to be a liquid layer decoupling the outer part of the planet from the interior part. And so we didn't get that information until the early 2000s. But it again confirmed what the magnetic field was already telling us, that there must be a liquid iron core inside Mercury.
Here's how much astronomy I've forgotten. Is Mercury tidally locked? Is it the same rotation?
So Mercury is in this 3-2 spin orbit locking. So it's not purely tidal locked. So it's not that one face faces the sun all the time. So 1 year doesn't equal 1 day. Instead, it's the 3-2 ratio.
Okay, but that's a very nice thing for the observations of wiggles and so forth. So we can figure out what they should be, what they are. Okay, good. All right, well, so then should we be a little chagrined that our theorists didn't predict something like that ahead of time? Like how good is the state of the art of we astrophysicists being able to say, here is what planet formation was like and therefore what planets should be like?
I like to think of it as, I think what we're learning is that the details really matter. And so you need to understand very specific details of a planet or a situation in order to understand what to expect. And that also means that more and more data actually really helps us. Every time we send a mission to a planet, we basically rewrite the textbooks about that, what we know about that planet, right? We aren't just refining sort of a number or a very specific theory. We're actually having to be very creative in coming up with new explanations for phenomena we see whenever we go to a planet now.
So let's just run through the menagerie. I guess we have the 4 inner planets. They're all terrestrial, but they're all also kind of different, which is weird and fun. And how are they different and how well do we understand why?
Yeah, great question. So I think this is something that actually I think we need to be very careful about when we're especially thinking about exoplanets nowadays, is that I would argue that the reason the 4 innermost planets are so different is because of really tiny circumstances, essentially. Mercury, why is it so tiny and have such a huge iron core? Probably because it got hit by a giant impactor very early on in its history. So that one giant impact completely changed the history of that body, right? Venus and Earth, so similar in terms of fundamental properties, mass and radius, so different in terms of living environment on the surface. And that's likely because Venus is just a little bit closer to the sun, so it's a little bit hotter and went through this runaway greenhouse process, right? Again, a tiny detail, a few degrees in temperature difference, right? Mars, lots of planetary formation models, when they try to create the inner solar system, they cannot make a small Mars. Mars is supposed to be big. The problem is, though, what we think is the reason for that is because if you include the outer planets, Jupiter ends up disrupting a lot of planet formation in the Mars region. And so it's hard to build a big planet where Mars is. So again, depends on what was near you. Did you have a Jupiter planet just outside of you? So there's lots of individual circumstances with each planetary body that ultimately determines its evolution. So I think that's really important to think about when, for example, we're looking at exoplanets and thinking about, is there life out there? What makes a habitable planet? Well, maybe it's not just about the distance from the sun or star and the radiation environment. They're going to be very specific details that determine whether a planet is actually habitable.
A lot of history and a lot of probabilistic events.
Exactly.
And so Venus and Mars are not that different in size from the Earth. They're slightly different distances from the sun, like you said, but are their interiors comparable in some way?
So Earth, Venus, and Mars are all roughly the same in terms of them having half their radius be about iron and the other half be rock. So in that sense, their interiors are very similar on a basic level. Yeah. Mercury's the outlier there in that it's mostly iron, very little rock. But we think we understand that from a giant impact.
How do we know about the interior of Venus? We cannot go down to the surface and do seismology.
So this is, I go on about this in my book a little bit. Venus is very frustrating, right? It's the worst planet out there.
It's right there. It's the closest planet.
Yeah, it's right there. But as planetary scientists, we've developed all these methods to study the interiors of planets. And almost every single one of them fails when it comes to Venus because of some reason or another, right? Venus doesn't have an active dynamo today generating magnetic field. So we can't use magnetic information to learn about its interior. It rotates so slowly that it's really hard to use information we can get from the shape of a planet. So, for example, the Earth is a little bit bulgy, right? Its equator is wider than its pole-to-pole region. All the planets are bulgy because they're rotating. Venus rotates so slowly that you can't really tell about how the bulge doesn't tell you a lot of information about the interior. Whereas because of the gravitational effects of it, when we look at the bulge of another planet, the shape of another planet, we can actually say something about the density in its interior. Venus, you want to put a seismometer on Venus? Sure, except it has to live in a completely hostile environment and it would basically melt right away. And no one can go down there because of the toxic atmosphere. So we can't use seismology to study Venus either, right? So all these wonderful ways we've found to discover what's going on inside a planet just fail when you get to Venus. So it's very frustrating. But we are making progress. I don't want to make it sound impossible. There have been very recent papers where people have been measuring kind of the slow rotation and a little bit about the precession rate of Venus to learn about what's going on inside the planet. And hopefully the new missions that will hopefully go to Venus will learn even more.
I mean, if an advanced alien civilization wanted to hide out in the solar system from us, the surface of Venus would be a great place to do it, right?
Yeah, if they can survive there, absolutely.
Well, they're an advanced alien civilization. I'm going to give them credit for that. But nevertheless, we do think that the interior is similar. Is there? I mean, or maybe there's no liquid part to the core because there's no magnetic field.
So that's interesting. So we don't know for sure, but we do think that the core of Venus is probably liquid. It's probably just not experiencing the motions, the convective motions that we have inside the Earth to create a magnetic field.
Okay.
And that might be because of the fact that it's not cooling fast enough to get convection to happen. Now, you start asking, well, why? Why wouldn't Venus convect? And it turns out a better question is, why on earth is Earth's core convecting? Because when you start doing the math, when you start looking at how much heat you would need to have escaping the Earth to generate a magnetic field, and you look at how much heat could actually have just been carried by conduction, the numbers are really close. And so we're just like barely able to convect on Earth. And so Venus might be more the norm. Venus might be the planet that's kind of cooling at just below the rate that would result in convection. The fact that Earth also has plate tectonics tends to be really important as a cooling mechanism for the planet. So imagine if you're trying to cool a cake, or let's say you have a baked potato. This is my favorite analogy. If you have a baked potato, you could just let it sit there and cool through conduction, or you can try to cut it up so that the interior gets exposed and cools down immediately. And plate tectonics is kind of like the cutting up of the potato because you're constantly exposing new material to the surface and descending cold material on the inside. So the fact that we have plate tectonics on Earth might be ultimately responsible for why we have a dynamo generating a magnetic field today, because it's a very efficient way to remove heat from a planet. Venus doesn't have plate tectonics.
And it's closer to the sun. Does that matter?
The reason we think that matters is because what happened in the atmosphere. So the runaway greenhouse ultimately removed all the water from Venus. Now, on Earth, yeah, we have water on the surface in our oceans and in our atmosphere, but we also have water inside the planet. And water can actually be used to lubricate the plates as they move around. So we think plate tectonics actually relies on having these volatile materials like water inside the planet. So it's possible that Venus doesn't have plate tectonics because it got rid of its water so quickly through the runaway greenhouse effect.
So this convection-conduction distinction is interesting. I want to make sure the audience gets it. So you're saying that if I have, a hot end of an object and a cold end, but it's a very smooth gradient. It's not that much hotter on one end, that much cooler. Then you can just transfer that heat by conduction. But if it's a dramatic thing, there's going to be swirls and convection.
Absolutely. Yeah, that's a great way to think about it. And I always like to go back to the pot on the stove, right? You got your porridge on the stove or something like that. If your burner's not on high enough, the temperature difference is not so big. So you don't have to transfer a bunch of heat through it. You can manage it through conduction. But as soon as you make that temperature high enough at the bottom, then the heat transfers much higher and you get the bubbling and the moving around of stuff.
So I'm going to guess that since Mars is smaller and further away from the sun and has less atmosphere, it does not have a liquid core. Help me out. Tell me I'm right.
So seismology actually told us that Mars does have a liquid core, but again, it's again the issue of the motions, right? So again, it's the lack of plate tectonics on Mars that doesn't allow it to transfer whatever heat it has coming out. But it's also very true that it's cooler nowadays. So even if it had plate tectonics, it's unclear if there would still be enough heat transfer to allow convective motions in the core.
Okay, so liquid but no convection as far as we know.
Exactly.
All right, good. And then there's like this radical change. When I was a kid, I always liked theoretical physics, but in my family's world, that was just astronomy. So they would give me these astronomy books. And so I was a huge believer that there used to be a planet in between Mars and Jupiter that got destroyed or something, but that's not right. We just go out there and we have the gas giants. And what you told me earlier was that there's more heterogeneity there than we originally thought.
Yeah, absolutely. So it's interesting to think about sort of our textbook model of what happens inside, say, Jupiter, right? You picture Jupiter as being this mostly hydrogen gas ball and probably has some sort of rocky core at the center. If you think about how planets form, people usually talk about that rocky core being about 10 Earth masses in size. That's when it got big enough that it could attract all the gas in the early solar system to become this giant gas planet. But then the Juno mission got to Jupiter, and through very careful gravity measurements inside the planet, was able to determine that it's not just this like center of rock and then this fluffy atmosphere around it. Instead, a lot of it is much more mixed inside. So there's almost like this gradient, this decreasing amount of rock as you go further and further out of the planet. So we talk about this now as Jupiter having this fuzzy core. It's not just this like sharp boundary between the rock layer and the gas layer. Instead, it's much more mixed. And we're trying to understand how that's possible and what it means for the formation of Jupiter.
I don't even know how to quite visualize that. Are there like little pebbles floating in the thick atmosphere?
So this is one of the hardest things to think about because we have to take materials that we're used to how they behave on surface of Earth and think about what happens to them when they're millions of degrees in temperature and millions of atmospheric pressures under that type of pressure, right? And it's just completely different. These things are usually, so the hydrogen and the rock is probably mixed. It's probably like a solution of some sort. It's just completely different way that materials behave under really high pressure and temperature.
Well, when you say rock, do you mean solid, or are you talking about the constituents?
Yeah, I think I'm pretty much talking about the constituents more. You're talking about higher density elements, higher mass elements like magnesium, silicates, probably some iron too. Basically anything that's not gas, not hydrogen and helium. Let me put it that way. Anything that's not hydrogen and helium for the center of giant planets, we probably talk about as rock.
Okay, so the fuzzy core, what kind of phase is it in?
Well, that's an interesting question. Like we're used to on the surface of the Earth just thinking about liquids, solids, and gases. But when you go deeper inside planets, it's probably accurate to call it a fluid. It's not really a liquid. It's not a gas. It's not a plasma. It's in that weird phase space where the properties of the material can behave very differently.
Have we sent probes just diving into Jupiter to see how long they last?
We have. So we sent one probe into Jupiter with the Galileo mission. I can't remember how far deep it went, but very much just the outer part of the atmosphere, right? Again, just like it's hard to dig inside the Earth, it's hard to go under high pressures inside gas giant planets as well. But it was a really interesting probe because one of the main goals of it was to measure the amount of water in the atmosphere of Jupiter, because water on Earth, for example, is so important to determine what happens in our atmosphere in terms of storms and things like that. And it just so happened to descend in Jupiter in like the driest spot in Jupiter's atmosphere. So we measured like no water whatsoever.
Too bad.
So, things happen. But yeah, so there was also, this is why probes can be so important though, because they can give us kind of like real in situ data from a particular region. But you generally want a lot of them or more than just one spot so that you can get some sort of more general understanding of the planet.
Is there any prospect for a probe that will sort of dive in but then come back out?
Not for the giant planets, no. Maybe the closest analogy to that, it's not a probe, but it also happens to be my favorite mission to think about in the future, is the Dragonfly mission that's planned to go to the moon Titan. So Saturn has this moon Titan, very cool moon. And one of the amazing things about the moon is it has an atmosphere very similar to Earth's in the sense that it's mostly nitrogen, and the pressure at the surface is about 1.5 bars. So 1.5, the pressure of Earth's atmosphere.
Okay.
So in that sense, Titan's atmosphere is very much like Earth. It's a much colder planet. But the other cool thing about the fact that it's a moon, it's small, its gravity is really low.
Yeah.
So dense atmosphere and low gravity means it's really easy to fly. So we are sending an octocopter, something with basically 8 helicopter blades, that is going to land on the surface of Titan, do a bunch of science at a particular location, then fly up again, look for somewhere new to land, go travel to that spot, land again, do a bunch of more science, and do a bunch of these kind of traverses across the surface of Titan. So it's the first mission where we'll have in situ information at more than one location over a large distance, right? We aren't talking about small rover distances like on Mars. We're talking about hundreds of kilometers of travel on the surface.
Because the atmosphere is thicker than Mars, so it's easier to fly.
Exactly, yeah.
When is this going to happen?
Basically you could put cardboard on your arms and flap them and you could fly on Titan.
There's probably other obstacles to doing that, but yes, that's very evocative. So when is this scheduled to occur?
So good question. So the mission is in development right now, probably launching sometime in the next decade. Then it takes
be patient.
Some amount of years to get there and so forth.
Okay.
So
good.
I would be thinking late 2030s by the time this will kind of send us back data that will be really cool.
And even though we've had a pretty good track record of late with things like this, it's always possible the thing just fails, right?
I mean, I'm scared to say it. Yes, of course, it's always possible that something could fail. But the scientists who are working on this, it's always amazing to me how many of the missions that we send out to the planet succeed the way they do, because there's so much that could go wrong, but there's so much work done to really ensure that nothing goes wrong, right? So it's quite amazing to me, the feat of the engineering and science that goes into every single mission we send out.
So back to Jupiter, I know that there's metallic hydrogen taking up a lot of Jupiter and liquid metallic hydrogen. And so is that like a little fun part of the inner structure, or is that most of Jupiter?
That is most of Jupiter. So again, kind of a great example of hydrogen, what we think of as hydrogen on Earth, just as gas you might expect. Put it under enough pressure, it becomes a metal. So it's actually a really good electrical conductor. And this happens at about, let's say, about 6,000 or 7,000 kilometers deep. So about 10%, you go 10% into the planet, and poof, you get this phase transition. You're in metallic hydrogen. Now, metallic hydrogen's a great electrical conductor. That's what's generating Jupiter's magnetic field. Yeah. So rather than a liquid iron core in Jupiter generating the magnetic field, you've got this giant metallic region inside Jupiter generating its immense magnetic field that we see.
So good. That's a success story for the theory and experiment combining, that it all fits together. And the other thing that maybe this is not fair because you're an interior of the planet person, but I'm always amazed at how colorful and stripy Jupiter is. Like, why hasn't it all just mixed together by now?
Yeah, this is a great question. First of all, I love the fact that the color, so hydrogen's a clear gas. So if Jupiter were pure hydrogen, we wouldn't see any colors at all.
Exactly.
So all the colors we see are from like tiny bits of kind of pollution, I would say, like in the atmosphere of these things like ammonia and sulfur and stuff like this that are floating around that we can see. The stripiness is really great, and because it shows us an important concept that's hard for us to kind of put our minds around, and that's the fact that rotation is really good at kind of separating regions inside a fluid. So if you spin a fluid, it's really hard to get it to mix on the inside. And this is a result of the forces that occur, the Coriolis forces, and how they affect fluids. So the fact that we have these bands, these stripy bands, is almost a direct result of the fact that we have spinning fluids and they don't mix when they're spinning that fast.
And just so people know, Jupiter's spinning really fast.
Jupiter's spinning really fast. Day on Jupiter is what? It's like 10 hours or something like that.
Yeah.
So
and it's much bigger than the Earth. So that's very fast indeed.
Yeah.
And Jupiter was always my favorite planet. I would like to go visit Jupiter someday. But then there's Saturn, which is, comparable in some ways, but very different in others. It doesn't have quite the colorful stripy bands that Jupiter does.
Yeah, Saturn's interesting because although it doesn't have as many observable bands, it does have these, we saw with the Cassini mission, it has these amazing storms at the poles. So this hexagonal feature, I don't know if you've seen this hexagonal storm at the poles, right? And so there's these great kind of fluid waves that are occurring to cause that pattern. The winds on Jupiter are actually very fast. It's just that they're not as stripy. There's not as many of the bands that go around the planet.
You said Jupiter means Saturn?
I'm sorry, but Saturn again,
right?
Giant planet, a little bit smaller than Jupiter, still has metallic hydrogen on the inside, generating a dynamo and a magnetic field. The rings on the outside, the amazing thing about Saturn to me is that you've got these gorgeous rings, and we can, you can see them in a telescope, but there are waves in those rings that are actually caused by motions inside Saturn itself. So we can use the rings as a probe of motions going on inside Saturn.
And what do we learn from those waves?
So what we've learned from that is that the innermost part of Saturn is actually what we call stably stratified. It doesn't have this convective motioning happening in the deepest part of Saturn because there are these gravity waves, these kind of like what you would expect when you see like the surface of like the ocean or whatever, kind of move up and down. There are these gravity waves, but it's not circulating like convecting motions are. So that's one thing we learned from the rings.
I know that there's an attempt in some circles to police the language of gravity waves versus gravitational waves. Gravitational waves we detect from black holes in spiraling, but gravity waves are motions in planetary interiors.
Yeah, I can tell you that as someone who kind of grew up kind of doing physics and astronomy and planetary science, that was very confusing to me at all.
Very, very different things. But otherwise, Saturn and Jupiter kind of related to each other qualitatively?
Yeah, qualitatively, Saturn's a bit smaller, so the pressures are a bit lower inside, the temperatures are a bit lower, but a lot of the same, the physics is the same.
But then Uranus and Neptune are actually kind of different.
Yeah, Uranus and Neptune seem to be completely different beasts. So they seem to be what would have happened if you had, while you were building Jupiter and Saturn, but you didn't get big enough, fast enough to attract a bunch of gas. So instead, you've got these rocky, icy balls left with a little bit of gas on top. We think they're mostly stuff like water, although it's really hard to actually figure out what goes on deep inside these planetary bodies. Their magnetic fields are completely different than any of the other planets in the solar system. So rather than having this nice dipolar field like we have on Earth with like a North Pole and a South Pole, they're multipolar. They have a bunch of North and South Poles all over the place. So we spend a lot of time trying to understand why that is. But also it's a great kind of test bed for what happens to water when it's under really high pressure and temperature. And you get really cool new phases of water. You get something called superionic water, where the oxygen atoms become a lattice and the hydrogen atoms just flow through the oxygen. Just really weird stuff happens at high pressure and temperature when you have water.
And is this from data or from theory?
So it started to be from theory, but very recently, in the past, say, 5 years, we actually now have experiments that can take materials at some of our biggest particle colliders, and you basically hit a material with a big shock wave, and boom, you put it under really high pressure and temperature, and we've actually created superionic water in labs here on Earth now.
And I know that, I forget whether it's purely hypothetical for exoplanets or even for our outer planets, but people love the idea of diamonds in the planets, yes. Right? Either, diamond rain or icebergs or something like that. Is that a Uranus and Neptune phenomenon? So
that could be a Uranus and Neptune phenomenon. So here's the thing. In addition to water, there are things like methane, CH4, right? So carbon-based elements out there. And so you start asking, what happens to CH4 when you put it under high pressure? And we know about the diamond phase of carbon, even here on Earth. You put carbon under enough pressure, you're going to get diamond. And so that's likely to happen inside Neptune and Uranus as well. The question is, does anything weird kind of happen? And it turns out that if we understand the exact mixture of, like, say, water, ammonia, methane inside the giant planets like Uranus and Neptune, the carbon could actually separate out from the other materials, and it's heavier, so it could sink. And so there's a theory out there that you would actually have a diamond sea kind of in the deep interior of Uranus and Neptune. And an interesting thing about diamond is at the melting point, it has the same property that water does at the surface of the Earth, where the solid phase is a little bit less dense than the liquid phase. And so you could have diamond icebergs on the diamond sea that float on it, just like water icebergs or float on our ocean. So some interesting things to think about what might be happening in Uranus and Neptune, and also on exoplanets.
Is that right below a sort of gaseous layer?
So that might be below a gas layer, but also below a water layer, a mixture of things like water, ammonia, methane, but just certain pressures and temperatures where suddenly stuff separates out. So you're talking about, we don't know exactly the depth of this, but let's say think about roughly halfway through the planet or so.
This is going to wreak havoc with the world's diamond markets once we actually start excavating these icebergs.
Well, you'd think so, but let's be honest here. We can actually make diamonds in labs nowadays.
Yeah,
the only reason diamonds are expensive is because people are trying to stop them from being made in labs and to go make them something that's hard to get.
That's right.
No reason to go to Uranus and Neptune to get diamonds. We could just make them in labs and sell them for $1 each. Right? So.
Again, I don't think you're maximizing your grant money potential here by telling the truth about diamonds. So, then I guess we should give a shout out to all the little tiny things in the solar system, whether it's dwarf planets like Pluto or asteroids or hyperbelt objects, et cetera, et cetera. There's an enormous array of different kinds of ways that matter comes together in our solar system.
Absolutely. And I love the small bodies in the solar system. I absolutely love, because they're basically the ingredients that created the planets. And so imagine you make a bunch of cookies, for example, and you show up at someone else did, and you show up at their house and they're like, here are a bunch of cookies, eat some. And you'd like to know what they're made of, because maybe you have an allergy.
Yeah.
But for some reason, they don't tell you, right? One way you could figure out what they're made of is by looking at kind of the remnants of stuff left on the counter where they were just made. So you might see some sugar floating around somewhere, some butter stuck on the counter or whatever, right? And that's exactly what the asteroids and comets and Kuiper Belt objects are. They're leftover ingredients of planet formation. And so we can really learn a lot about how Earth and the other planets formed by studying these leftovers.
And comets, I presume, also, which have a lot of the volatiles. Is it true that comet collisions contributed to a lot of the atmospheres in the inner planets?
So that's a good question. The short answer is we don't know. We do know that comets have a lot of water, and that comets end up on these weird orbits sometimes that could bring them to the inner solar system, so they can deliver water to planets. But when we look at something called the D to H ratio of comets, so how much of the two isotopes of hydrogen and H2O in water, the deuterium isotope, the heavier isotope, there's like a particular signature that our oceans have of this D to H ratio that tells you something about where our water is from.
Right.
And it doesn't really match exactly what comets we've gone to, when we looked at their ratios, weren't the same. So it might be a mixture. It might be a little bit of comets. It might be a little bit of some asteroids that we know also have some water. And it might be that a lot of our oceans and stuff just actually came from water that was able to be stored inside of Earth that essentially got outgassed from volcanoes, for example.
So there's still lots of learning to be done when it comes to the solar system. And I guess we haven't even had a chance to talk about the other 100 billion planetary systems or whatever in our galaxy. But what is the current vibe amongst people who think about exoplanets? On the one hand, very exciting. We've found all these planets, that we're going to find a whole bunch more. On the other hand, we've kind of been humbled at how different our predictions were than what we've actually seen. So where are we kind of landing right now?
Yeah, 100% agree with you. And I think what this is it's a major opportunity, because now it used to be the case that if you wanted to come up with a theory for something on Earth, you'd say, okay, how can I test this theory? Well, we can't build another Earth and test it, see if it happened there. So we'd have to look at the other planets in our solar system. And if we had a good explanation about, if Earth has X, then Y must happen, it better also explain why some other planet that has X also had Y happen. But you only have 8 other planets and 7 other planets and some other small bodies and stuff. But now we've got these thousands of exoplanets out there. And it's just an incredible test bed for all the theories that we use to develop for how our own solar system and our own Earth formed. So I think it's an immense opportunity. And it means that we have a lot of learning to do about what's possible.
Well, your research career spans this era where we found all these planets. I mean, what is the single most surprising thing to you that we've learned so far?
Oh, gosh. Single most surprising thing. I don't know if anything is. I think find that first exoplanet orbiting sort of a live star, this giant hot Jupiter,
right,
so close to the parent star. I think that was a major surprise, right? I think for everyone, not just me, right? But and the fact that it showed us how much planetary migration really matters, that planets can move around, I think that's still the most surprising.
And, we always get down to the end of the podcast where we let our hair down and have fun. So life on these other planets, what are your prospects?
So someone the other day asked me if I had to bet what planet or object will we find life on next. And I went with Titan.
Titan?
So this moon of Saturn as the place we're most likely to find life if it's out there. So the key thing here is you think about, as far as what we know about how life formed on Earth, where are the ingredients and the conditions right for it to happen? So you're looking for a place, turns out that liquid water seems to be important. Having an energy source for the life seems to be important. Having complex molecules around that can use that energy source along with the catalyst environment of liquid water to build larger and larger molecules. And the place where that all seems to be there is on Titan. So you've got this water ocean underneath the surface of Titan. You've got a surface that's basically formed out of hydrocarbons. So it's a bunch of organics on the surface. And you have energy sources from tidal interactions and so forth on the interior. So I'm guessing we find it at Titan.
Any chance for life on the diamond ocean of Neptune?
If so, we're talking about life that can live at much higher temperatures and pressures than anything we have found on the Earth. So it's probably something that we wouldn't fully understand, but it would be cool if it was there.
That's what makes it exciting. Looking forward to what happens next. So Sabine Stanley, thanks so much for being on the Mindscape podcast.
Thanks for having me here.